When we have collisions, that's when two moving objects make contact with each other. So kind of like the billiard balls that we had in the earlier idea. Conservation of momentum is used to analyze all possible collisions. And Newton's third law is also useful. It tells us that the force of body A on B is going to be equal and opposite to the force by body B on A. So if we have a collision, this could be the collision between two billiard balls, and this would be the free body diagram. The only unbalanced forces are from within the system, so we can have conservation of momentum. We ignore all external forces. The time frame of the collision is very short. And remember, the forces of impulsive forces are typically high force, short durations. We have to know two types of collisions. There's elastic collisions, which you might call hard collisions. That would be like billiard balls colliding. There's no deformation. Nothing breaks or changes shape. So no kinetic energy is lost. So in an elastic collision, kinetic energy is conserved. Inelastic collisions are where you have some sort of deformation and you will lose kinetic energy. We have a third type of collision. We call it perfectly inelastic, and that's where two objects collide and stick together. They become one object. So there's a deformation because have two things become one, and you also have a loss of kinetic energy. Kinetic energy only remains constant for a system in an elastic collision. So in a perfectly inelastic collision, it's the simplest type of collisions because there's only one velocity since there's only now one object. Remember, it's two objects colliding and sticking together. We lose kinetic energy, and it's basically the reverse of an explosion. Okay, so now here's a problem where we've got that same situation. We've got an 80-kilogram grandma about to collide with a 40-kilogram child at rest. We want to know what the velocity of the kid is and grandma after the collision. Well, conservation of momentum would look simply like this: subscript G for grandma, K for kid. And I've done a prime superscript for velocities after here. And remember that the kid and grandma move together afterwards, so we said this would be an easier problem since their masses are combined. When you substitute in your values, the kid has no velocity, so you're going to have a very simple expression for velocity to solve, substituting in the masses and the velocity of grandma before the collision, and you're going to get 4 meters per second when you do all the math. Now there's another way to think about this, and if you follow along, this is great. If not, don't worry about it. But look at the system as a whole, and I'll show you this approach in the next two problems. This is a great approach for perfectly inelastic collisions. The system as a whole, you've got 120 kilograms of mass. So the moving mass after the collision increases from 80 kilograms to 120 kilograms. I'm just taking grandma moving at 80 kilograms beforehand, and afterwards grandma and kid is 120 kilograms. So that's an increase of 33%, a 1/3 increase. So after the collision, the velocity must decrease by that amount, by 1/3 or 33%. So since 33% of 6 meters per second, or 1/3 of 6 meters per second, is 2 meters per second, we're going to decrease from 6 meters per second to 4 meters per second. So I can reason it through with kind of a ratio type of approach as well. I show you this. So here's the same idea. Train of mass 4m is moving 5 kilometers per hour. It couples with a flat car of mass m at rest. Notice we're not giving the mass. What is the velocity of the cars after they couple? Well, same approach. One mass moving afterwards. Substitutes and realize no masses, so we're carrying this m, 4m here for the mass of the train car, 4m plus m for the moving mass after the collision. So that's 20 masses times the kilometers per hour equals 5 masses times the velocity after. So the masses will cancel out. 20 divided by 5 is 4 kilometers per hour. Or the moving mass increase was a 20% increase, so the velocity mass is going to decrease by 10%. Same idea here with the fish, and I'll do my second approach first. The fish swallows a stationary fish, which is 1/3 of its mass. So what's the velocity of the big fish after dinner? Well, you've got the moving mass increasing by 25%, so the speed has to decrease by 25%. So 25% of 2 meters per second is a half a meter per second, so the final velocity has to be 1.5. Or you can just do a more formal approach. 2 meters per second times the unknown mass is equal to the new velocity times 4/3 of the mass. We have mass 1 plus mass 2, so that's a mass plus 1/3 of a mass, which is 4/3 mass. So just solve, divide by 4/3 or multiply by 3/4, and get 1.5 meters per second. All right, so an elastic collision, after an elastic collision, there's still two objects with two separate velocities. The kinetic energy of the system will remain constant before and after the collision with elastic collisions. So you have two basic equations that must hold for all elastic collisions. The sum of momenta before and after has to be constant, so momentum is conserved. And all of the kinetic energies before and after must also be equal, the sums of them. So we have a pool ball traveling at speed v, striking a second pool ball at rest, such that the first pool ball stops completely. We want to show that the second pool ball must now have the same speed v, assuming an elastic collision. Well, if we conserve momentum, we just had the momentum of ball 1 before equaling the momentum of ball 2 after. Since masses are equal for pool balls, the velocity before equals the velocity after. Very easy to show with conservation of momentum. If we do it with conservation of kinetic energy, in a similar sense, we just have the kinetic energy of one ball before equals kinetic energy of a second ball after. So we can substitute in the kinetic energy expressions. We can cancel the masses. When we take the square root, we get a plus or minus value, but we have to choose the positive velocity when we understand that momentum has to be conserved, and so the direction of momentum can't change. So we would show the same thing with conservation of energy. So here's something now with numbers. We've got a 500-gram cart on an air track striking a 1,000-gram cart at rest. We want to know what are the resulting velocities of the two carts, assuming an elastic collision, and the first car is moving at 2 meters per second when the collision occurs. Now what an air track is, it's like the carts and ramps that you have in class, but it actually are floating on air. I have a large one, but it's really loud, and I would only bring it out for demonstrations, but I have to shout at you to show you what I'm talking about. So before and after, let's set it up. Before, it's only the first cart moving. After, they're both moving. So 500 grams is a half a kilogram times 2 meters per second gives me 1 kilogram meter per second of momentum before. Afterwards, I've got a half a kilogram of the first cart moving at velocity v1 and 1 kilogram times velocity 2. But notice this is one equation, two unknowns. It's not enough to solve the problem. So let's bring in conservation of energy. Now we've got two equations, two unknowns, and I could substitute in the masses and solve for the kinetic energy on the left, since I know the velocity on the left. I've got to solve these simultaneous equations somehow or other. You very rarely would have to do this on the exam. I would get the first velocity to be negative 0.67 meters per second and the second to be 1.33. What would happen in this case here? Three equally strong, equally massive astronauts play a game where the first astronaut throws the second towards the third, and the game begins. Think about what would happen to the motion of these astronauts as the game proceeds, and assume that each toss results from the same sized push. And how long would the game last? We'll look at this problem in class. So we're going to do a lab in class, and I'm going to have a video preview for it. But what you're going to do is 3 or 4 trials trying to demonstrate all 3 of these types of collisions. Perfectly inelastic, so they're going to stick together with equal masses. Perfectly inelastic with unequal masses. And then an elastic collision with equal masses. And I'll show you how to do this in the video with the cart. And then if you have time, you can do an elastic collision with unequal masses. So you're going to turn in data, calculations, and your results that you find here. Okay, I'll need to see all of these different things and a calculation of momentums before and after. I want you in your calculations to show me that momentum is conserved. And also the kinetic energies before and after the collision, showing me that in only the elastic cases, kinetic energies are conserved. Now, two-dimensional collisions, I made a statement earlier, I think 95% of the time we'd be doing one-dimensional or linear momentum. You've seen a couple of things where we find momentum of a system at 2 dimensions when we had the sprinters going the different directions and the explosion. And you have two-dimensional collisions, momentum in the x direction will be conserved. It's a separate problem, kind of like what we did with kinematics. Momentum in the y direction is also conserved. So we think about this as two different problems, and we treat them independently. Ignore x when calculating y, and ignore y when calculating x. So this website can give you a simulation of this. I encourage you to look at it. Here's a problem that we can solve. You might want to jot these down because the solution is on the second page. But what you have is you've got a 2 kilogram ball moving at 3 meters per second horizontally only to the right in the x direction. There's an 8 kilogram ball at rest waiting to be hit. After the collision, the 2 kilogram ball scoots off at a 50-degree angle to the right above the horizontal axis. The 8 kilogram ball moves off below the axis. Now we don't know what that angle is, and we want to find what the velocity of that 8 kilogram ball is after the collision. You may think this is a difficult question, but it's easier than what it looks. Solve first in the x direction. Before, remember, it's only the 2 kilogram ball moving. So its mass is 2 times its velocity is 3. After, you have the momentum of the 2 moving balls. The original 2 kilogram ball has a velocity of 2 meters per second times the cosine of 50. We must take the horizontal component of that. The 8 kilogram ball has an unknown velocity in the x direction. We'll call it Vx. So Vx is our only unknown. We can substitute and we can solve and get 0.429 meters per second. Now that's not the velocity of the 8 kilogram ball. It's the velocity of it in the x direction. Now let's go to the y direction. Remember that the ball, the 2 kilogram ball, was moving horizontally, so there's no momentum in the y direction. So before, the left side of our momentum conservation, it's 0. Afterwards, we've got the 2 kilogram ball times its 2 meters per second times the sine of 50. That is the vertical part of its velocity. We're subtracting from that the 8 kilograms times the y momentum because that momentum, and you can see in the diagram, is down. So we can solve for Vy as being 0.383 meters per second. So understand what you now have. An x velocity of 0.429 meters per second coupled with a y velocity of 0.38 meters per second. These two velocities are right angles, so we can get the magnitude by the Pythagorean theorem, which is 0.575 meters per second. We can get the angle with an inverse tangent and get 41.8 degrees below the positive x-axis. And that's conservation of momentum in 2 dimensions. You will see it very little, probably more likely in a multiple choice question, although you will see this a little bit in a free response question on the test.